Okay, Assalamu alaikum students. How are you? I hope you will be fine and doing well. Stay blessed at your homes. Today study, we will discuss the topic of permanent polarization, that is ferroelectricity. It is a very important topic, just like a ferromagnetism. We have studied in our previous classes about the ferromagnetism, and we saw that in ferromagnetism, the domains are completely aligned and the material is already magnetized without applying the magnetic field. In the similar fashion, over here for the ferroelectricity, the material is permanent dipole, has a permanent dipoles, and it is a permanently polarized. It is the molecular field EM that is responsible for polarizing the individual molecules. Mean in the first of lecture of this chapter, we have studied about the molecular field and molecular field polarization. And we saw that EM, the molecular field, is the field that is completely responsible for the polarization of the individual molecules. And we have discussed in our previous lectures, in the first lecture of this chapter, that relationship between EM and the macroscopic electric field E is given by our equation 5.7, that was EM is equal to E plus 1 over 3 epsilon naught P. Means the molecular field was equal to the macroscopic electric field E plus 1 over 3 epsilon naught P. In most cases, the polarization is proportional to E, so that EM vanishes when E goes to 0. Means molecular polarization becomes 0 when the macroscopic polarization becomes 0. But under the certain conditions, this equation 5.7 EM is equal to E plus 1 over 3 epsilon naught P is also compatible with the permanent or spontaneous polarization, where E is set equal to 0, then EM is equal to 1 over 3 epsilon naught P naught. This is our equation number 5.25. So in this sentence, in this concept, we have talked about permanent or spontaneous polarization that is always present in the material. For that case scenario, E is equal to 0. So the equation of 5.7 becomes EM is equal to 1 over 3 epsilon naught P naught. Or in other words, if polarization P naught exists, what is P naught? Yesterday we studied in the equation 5.22a, P naught is a permanent polarization. So this P naught exists. If this P naught exists, it will create an electric field at the molecule which tends to polarize the molecule. So in equation 5.25, if P naught is present, then it will create an electric field at the molecule that will polarize the molecule. And to be sure, a polarizing field exists, but if this field gives rise to a polarization different from P naught, then the solution is not self-consistent. Therefore, if n is the total number of molecules per unit volume, then permanent polarization P naught is given by n alpha Em. We have discussed already that P naught is equal to alpha Em, where alpha was polarizability, and that was for the one molecule case. And if there are n number of molecules, then P naught will be equal to n alpha Em. We have seen in our previous equations. Over here, for Em, get the value from 525. Equation 5.25, this one. Put here in this equation, we will have n alpha over 3 epsilon naught P naught. P naught is present on both sides. So you can say that either P naught is equal to 0 or n alpha over 3 epsilon naught is equal to 1. Why 1? If you bring this P naught on the left hand side, P naught will be cancelled out with P naught, then n alpha over 3 epsilon naught will be equal to 1. So this is a very critical condition for the ferroelectric materials. Thus the condition for a permanent polarization is equation 5.27. So equation 5.27 is what? This is the condition for a permanent polarization. Means if n alpha over 3 epsilon naught is equal to 1, then our material will be permanent polarized. And if it's less than 1, then it will be not permanent polarized, mean it will not be ferroelectric. It can be paraelectric or dielectric material. For most materials, n alpha over 3 epsilon naught is less than 1, and ordinary dielectric behavior results. As I have told you that if n alpha over 3 epsilon naught is less than 1, the material will not be ferroelectric. It can be dielectric or it can be paraelectric. Yeah, you can say that it behaves like ordinary dielectric material. In a few crystalline solids, however, condition in the equation 5.27 is met. Such materials are called ferroelectric because their electrical properties are analogous to the magnetic properties of the ferromagnetic materials. Means there are some materials available, crystalline solids, in which this condition n alpha over 3 epsilon naught is equal to 1 is met, and for these materials who obey the condition of equation 5.27 are called the ferroelectric materials because their electrical properties are analogous to the magnetic properties of ferromagnetic materials. The best known example of a ferroelectric material is barium titanate, BaTiO3, which exhibits a spontaneous dipole moment at temperature below 120 centigrade. Means this material, barium titanate, becomes ferroelectric when temperature decreases below the 120 centigrade. And when the temperature rises and crosses 120 centigrade, then it becomes paraelectric or dielectric material. So this temperature is called Curie point of the material. For this specific material, BaTiO3, for this material, 120 centigrade is the Curie point. Means below this temperature, the material will be dielectric and ferroelectric, sorry, and above this temperature, it will be dielectric. And the polarized state of ferroelectric material is relatively stable one and one that can persist for a long period of time. This statement may surprise us to some extent because a polarized specimen is subjected to its own depolarizing field, and depending on the geometry of the specimen, this depolarizing field may be rather large. So, the point is, in this sentence, the polarized state of a ferroelectric material is a relatively stable one and that can be persist for a long period of time. Means the domains, the dipoles in the material are aligned in the direction of electric field E, and they remain aligned for a long time and offers a permanent polarization of the material. But this also depends upon the dimensions of the material, and the depolarizing field is the largest for a specimen in the shape of a flat slab, polarized in a direction normal to its faces. And if we have a material in the shape of flat slab, then it will be polarized in the direction normal to its faces. Means normal to the upper and lower face of the slab. As we have seen that if the dimensions of the slab face are large compared with the slab thickness, then ED is equal to minus 1 over epsilon naught P. Means the length of the slab is larger as compared to the thickness of the material. If this condition is present over here, then depolarizing electric field of the material will be equal to minus 1 over epsilon naught P. This is our equation number 528. Actually, the high stability of a polarized ferroelectric is due to the fact that there is no depolarizing field on the specimen, even for the case of slab geometry. What is the reason for the stability of the polarized ferroelectricity? The reason is that there is no depolarizing field on the specimen. The specimen is polarized by placing it between parallel conducting plates that subsequently have a large potential difference applied to them. You place this ferroelectric material in between two parallel plates having a large potential difference. Means a high battery is connected to the both plates and the ferroelectric medium is placed between these two plates. In this process, the free charge from the plates will to a large extent be neutralized by surface polarization charge, as is also the case during polarization of a conventional dielectric. We have studied in our previous lectures for the dielectric that when dielectric is placed inside the electric field, then polarization takes place inside the material, and each individual dipole cancels the polarization effect of each other, and as a result the net charge on the surfaces reside. In the similar way, when we put this ferroelectric medium inside the plates, the neutralization starts to occur. Means inside the medium, the material gets neutralized. If the parallel plates are now brought to some potential by short circuiting them, the polarized state of the ferroelectric is still energetically favorable, so the free charge stays in place, still neutralizing the polarization charge. And this situation is sometimes like that shown in figure 5.5, where the free charge is held in place by the surface polarization charge. We come to the figure 5.5. Look, it's an excellent presentation of this situation. When you place the medium, ferroelectric medium inside the plates, and the charge resides on the surfaces of the battery, and permanent dipoles are present inside the material, but the individual plus minus charge will cancel to each other inside the medium, where E is equal to 0, and the only surface free charges will reside on the medium, plus and minus, both on both plates will be present. Other material will get neutralized. The macroscopic field inside the ferroelectric is 0, as we have discussed. Furthermore, the external electric field is 0, and it is difficult to distinguish the polarized specimen from a conventional unpolarized dielectric material. Means when you do not apply the external electric field, then you cannot differentiate between this ferroelectric material and dielectric material. Both behave with a similar behavior as shown in figure 5.5. And if a large potential difference of the opposite sign is now applied to the plates surrounding the polarized ferroelectric, the specimen will change its polarization, and free charge of the opposite sign will flow to the plates from the external circuit sufficiently not only to neutralize the free charge already there, but also to neutralize a new polarization charge. So when you change the polarity of the battery, the neutralization will also occur, but the opposite kind of charges will be stored on the plates of the battery, and inside the material all the dipole will be reversed, and plus will become minus and minus will become plus for individual dipoles. Like here, this minus will be plus, this plus will be minus. For this dipole, this minus will be plus, and this plus will become minus. And similarly, for all the dipoles, it will occur. Thus, a ferroelectric slab between two parallel plates may serve as the basic element of memory device. So this is another application of the ferroelectric materials, that if you change the polarity, the charges will be changed and polarization direction will be changed, and it can be used as a memory storage device. It is capable of storing charges on the two plates surrounding the ferroelectric as plus minus or minus plus. The critical point is that only the charges will be stored on the plates, not inside. Inside the material, ferroelectric material is neutralized because each individual dipole will cancel to each other, and there will no charge reside, there is no charge available inside the material. And its polarization persists in the absence of an external electric field. Means even if you remove the electric field, the polarization will be present inside the material. And the number plus minus or minus plus may be read by applying a potential difference across the specimen. Mean when you give the polarity to the plates, you will get the information that either the plate was positively charged or negatively charged. This is the information stored on the plates. That is why it can be used for the memory device as a memory device. If the applied field is in the direction of the original polarization, no charge will pass through the external circuit. Mean you apply the electric field to this situation in the direction of the polarization, you will see no flow of the charge. And if the potential difference is opposite to the original polarization, a charge will flow through the external circuit as the polarization of the ferroelectric changes its direction. Means charges will flow through the external circuit. Mean information will be moved from the plates to another point if you apply the opposite charge, opposite battery to this geometry. A polarized ferroelectric is stable against a reversed electric field, provided this electric field is not too large. A polarized ferroelectric is stable against a reversed electric field, provided that electric field is not too large. Means if you do not apply a strong electric field, but the opposite electric field will not change the stability of the ferroelectric material. The condition is that applied electric field will not be so strong that it can destroy all the information stored on the plates. Figure 5.6 shows the complete curve of the polarization versus electric field. Yes, we come to the figure 5.6. It's over here. This is a hysteresis curve for a ferroelectric specimen. Just like a ferromagnetic material, we have studied the hysteresis curve, the hysteresis loop. In the similar way, this hysteresis loop is for electric field versus polarization. Mean if your material is polarized and you increase the electric field, it will move towards the right side in the first quadrant, and if you decrease the electric field, and it will become the saturated. And if you decrease the electric field and decrease up to zero, the polarization will not be destroyed, it will be present, at the stable point B. But if you reverse the direction of the electric field up to the point C, the polarization will be decreased and become zero for the negative of the electric field. Then if you even decrease more electric field in the negative direction, so increase the electric field in opposite direction, then it gets again saturated in the third quadrant. Means polarization will be in the opposite direction, will be negative. Negative means in a sense that it will be opposite to the original polarization direction, and it will be saturated. You again decrease the negative of the opposite direction, opposite electric field, and comes to a zero. The polarization will be starts to decrease, but at the point A it will be stable. And then again you increase the electric field, the polarization will start to decrease and will become zero at this point. And after increasing more electric field, again polarization in the original direction will be present and will be maximum saturated at this point. So this loop is basically called the hysteresis loop for the ferroelectric materials. It is evident that for low fields there are two values of P for each value of E. Yes, we have seen from the figure that for each value of E, we have the two values of the polarizations. A curve such that shown in figure 5.6 is called the hysteresis loop. Hysteresis means to lag behind, and it is apparent that the polarization vector lags the electric field vector. Means polarization is plays a role in on the front and electric field on the behind of the polarization. Points B and A are the stable configurations at E is equal to 0. Yes, we have seen from the figure that for electric field E0 over here, the point A and B are reached, and these are called the stable points of the for the polarization. They represent the polarization plus minus or minus plus respectively. The point that we have discussed previously for the memory devices, the polarization is basically stored memory on the plates, either minus plus or plus minus. And point C is the electric field that must be exceeded in order to reverse the polarization. Means if you want to reverse the direction of the polarization, you will have to exceed this point C. So this was our today's topic. That was about the permanent polarization, and we have studied the ferroelectric materials just like a ferromagnetic materials. In ferroelectric materials, the permanent dipoles are available that neutralize each other inside the material. And we have studied this hysteresis loop in a very good manner, just like hysteresis loop for the ferromagnetic materials. We have performed the experiments, and we have studied that polarized piece of the ferroelectric material can be used as a memory device. So, up till now, if you have any question, you can ask me. And if you have questions later on, yes, you can send me via my WhatsApp number in my description. You must like the videos and my lectures. Thanks very much. No question? Okay. Thank you. You can ask me later.